Imagine needing to control a large amount of electrical current, perhaps to power a motor or illuminate many lights, all with just a small electrical signal. This precise control is fundamental in modern electronics, and at its heart often lies a transistor, specifically an N-channel MOSFET, acting as a high-speed, efficient switch. To effectively choose the gate voltage for an N-channel MOSFET in switch design, you essentially need two critical voltage levels. One is a voltage for the on state, which must be high enough to fully turn on the transistor and ensure it operates in its ohmic or triode region, minimizing resistance. The other is a voltage for the off state, which must be low enough to completely turn off the transistor, placing it in cutoff and preventing any unwanted current flow. The core reason behind these choices lies in the MOSFET's fundamental physics and its operating regions, governed by its threshold voltage, often referred to as VDH. For an N-channel MOSFET, the gate source voltage, or VGS, controls the formation of a conductive channel between the drain and source. When VGS is less than VDH, no channel forms, and the MOSFET is in cutoff, acting as an open switch. When VGS exceeds VDH, a channel forms, allowing current to flow. To ensure a good on switch, VGS must be significantly greater than VDH, typically 2 to 5 times VDH or more, to drive the MOSFET deep into its ohmic region, where its on-state resistance, known as RDS on, is at its lowest. This minimizes power loss and voltage drop across the switch. Practically, when designing, you will select your on-gate voltage based on the MOSFET's datasheet specifications and your circuit's power supply. First, identify the VGS value that yields the lowest RDS on for your required drain current at your operating temperature. This ensures maximum efficiency. Next, ensure this VGS is compatible with your driving circuit, such as a microcontroller's output voltage. For the off state, a gate voltage of 0 volts relative to the source is usually sufficient to guarantee cutoff, provided it is well below the threshold voltage. A valuable insight for efficient design is the use of what are called logic-level MOSFETs. These devices are specifically engineered to achieve full conduction, or the lowest RDS, on, with a gate voltage compatible with common digital logic levels, like 3.3 volts or 5 volts. This eliminates the need for additional level shifting circuitry, simplifying your design and potentially reducing power consumption. Understanding the datasheet's graphs for RDS, on versus VGS is also critical, as it directly shows how effectively the MOSFET will switch at different gate drive voltages. By carefully considering the threshold voltage, the desired RDS, on, for your load current, and the capabilities of your driving circuit, you can confidently select the appropriate gate voltages. This ensures your N-channel MOSFET switch operates reliably and efficiently, providing robust control over your electronic systems and preventing common issues like excessive heat generation or unreliable switching behavior.